It's a great honor to be here for my 4th straight ATPESC. You're an awesome group, and my only regret is the state of the world that we're handing off to you with all of its challenges. But architectures, algorithms, applications, analytics, programming models, system software, libraries and tools, I/O, you get a lot of input these 2 weeks. And you might think, is my talk out of place coming on the architecture day rather than next weekend when most of the algorithms talks will be delivered? But in fact, I'm very happy to preview the algorithms space in the context of the great architecture talks that you've heard today. And from my lunchtime sampling, several of you are the algorithms people in your multidisciplinary groups. And this overview talk is for you, but so I emphasize were all the architecture talks that you heard today. So the tie-ins, we were instructed to make tie-ins to other ATPESC talks, and of course I've just alluded to the interconnected ecosystem that these various topics now constitute. Algorithms have to span diverging requirements. Architecture is heading towards more uniformity at the small scale for power efficiency. Algorithms are heading towards more irregularity for adaptivity, multiphysics, and so forth. And that increasing gap has to be spanned by people like us. So there's tie-ins to the vendor presentations that you heard, to the programming model talks that are coming up tonight and all through Thursday, and of course to the algorithms talks coming next weekend. So my motivation for a lot of what we do in the Extreme Computing Research Center has to do with the hardware that we are dealing with. Now, I actually don't consider either of these systems extreme. These are commodity, petascale systems. They're not that hard to program well the way we've been doing MPI-based programming for the last 25 years. But if you follow the trends towards the future, you see some dark clouds on the horizon. Between 2009, when we got our first system, and 2015, when we refreshed it, we were able to improve the peak petaflops by a factor of 33, which is about right. That's the square root of 1,000. Every 10 years, we get a factor of 1,000 at the top of the top 500 list. Power improved. Power only went up by a factor of 5.5 out of that 3.3. So the efficiency of gigaflops per watt went up nicely. But nothing else kept up. The amount of memory went up by a factor of 12, but that was off the pace, and it ruined the Amdahl-Case ratio by a factor of 3. And in the new machine at the top of the top 500 list, the Chinese Taihu Lite, the Amdahl-Case ratio has really gone through the bottom. I/O bandwidth went up by a factor of 20, but again, not keeping up with flops. Storage went up by a factor of 6.5, but not keeping up with flops. So in many ways, the dimensional and dimensionless ratios of our hardware are getting worse for algorithms people. And here's a quote from what many believe to be the world's greatest hockey player. A good player skates to where the puck is, while a great player skates to where the puck is going to be. And that's what I consider our agenda. Algorithms for where architectures are going to be. Now, such algorithms may or may not be the best today, but the hardware trends can be, they can be extrapolated, and you can infer algorithmic sweet spots, or what we might say are algorithmic sour spots, but they're the best that we can do. So there are many examples, and I won't be presenting these examples. I'll just list them and give a sentence or so for each one, just to give you a flavor of what sort of directions I'm talking about. Way back in the 1970s, there was an algorithm called cyclic reduction, which for Poisson solves, if you had constant coefficients, gave you an order n log n. You used FFTs to rediagonalize the Schur complements that came up as you recursively subdivided your original large PDE domain. But if you have variable coefficients, that FFT is fragile. But it turns out that the resulting order n squared complexity can be addressed with what are called hierarchically low-rank matrices. The Schur complements coming from the block elimination, although they have full rank, off their diagonal, they have very low rank and can be well approximated using SVDs on small blocks. So you're doing lots of flops, but it's all local. It's all in cache or in local memories. And you can reduce the complexity back to order n log n, just as if you had constant coefficients. Fast multipole method is a 30-year-old algorithm that's an O of n solver for potential problems, electrostatics, and not only that, Helmholtz, you can use it for linear elasticity, Stokes flow, and so forth, anything linear with a nice Green's function, but it has a bad constant relative to multigrid if it's used at high accuracy as a solver by itself. But if you use it at low accuracy, if you just take a few poles in the expansion, it can be very efficient as a preconditioner, and it's much less synchronous than multigrid. So it has high potential for future highly concurrent architectures. The QR weighted Rayleigh polar decomposition leading to a new singular value decomposition, that's a 3-year-old algorithm. It performs a lot more flops than the standard scale-pack eigensolver. But you can also get an arbitrary amount of dynamically schedulable concurrency. There's a recursive subdivision in the creation of the polar decomposition, which then leads right away to the SVD. And it already beats the state of the art on GPUs, even though doing many more flops. Multi-core wavefront dynamic tiling is a stencil evaluation library that reduces memory bandwidth pressure on multi-core processors. Instead of each core needing its own piece of cache, which is reserved for its own use, the threads can actually share cache blocks very effectively. BDDC, balancing domain decomposition with constraints, is a preconditioner that's well suited for high contrast elliptic problems. For instance, reservoir flow under the earth where you might have 10 to the 6, 10 to the 12 variation of permeability between different rock types. And it does a lot of local flops. In fact, at every interface in the domain that you are dividing your problem into, it solves a generalized eigenproblem. But all those flops, they're just Cholesky, they're almost free. They don't require going to memory a lot. And since it reduces the outer iterations of the conjugate gradient or GMRes method to an initially dynamically choosable amount. I mean, you can pick the condition number. Whatever condition number you pick, you take the eigensolver to a certain number of eigenvectors in your subspace. And this is now part of the PETSI library that you'll be hearing more about next weekend as a preconditioner option. Then there's, for instance, the multiplicative Schwartz precondition inexact Newton method, which is a new nonlinear preconditioner that replaces most of the global synchronizations of Newton with local problems. There are still some infrequent global synchronizations, but there's 2 ways to handle synchronization: make it less global or make it less frequent, and this one does a little bit of each. So the motivation for these kinds of algorithmic adaptations to architecture, the roots of them in my own awareness can be found in the exascale roadmap, which was lead authored by Jack Dongera and Pete, who just introduced me. And in fact, you'll be hearing from 8 of the co-authors of this report throughout the week, so don't miss them. The uptake from these meetings, which looked at every aspect of exascale computing, from the point of view of an algorithms guy, obtaining the next order of magnitude, we now have a 125 petaflop system in China. Obtaining the last order of magnitude towards exascale, we'll need an order of magnitude flops per watt. The target, as you've heard, is about 50 gigaflops per watt. Today, the best is 6.7 gigaflops per watt. And there's already a tendency towards less memory and less memory bandwidth per flop as a result of that power pressure, because memory and memory bandwidth are where most of the power actually go. Power may be cycled on and off, clocks slowed or speeded, depending on compute schedules and dynamic thermal monitoring. This makes performance per node unreliable, as you heard from Pete this morning. Equal work is not equal time. This spoils any algorithm that's dependent on regular global synchronizations. And also the reduction of power per flop and per byte transferred may make computing and moving data less reliable. If you're interested in engineering efficiency, you may tolerate some lack of reliability in the hardware if you can make it up in the software, if you can design algorithms that are robust with respect to some errors. For instance, instead of error correcting memory, which writes and then reads back and then does a comparison, you may say, heck, that can write. If it's just going to spoil my residual at the next iteration, I'll detect that residual. I'll restrict it. A small amount of each program typically needs to have reliable memory and reliable flops, but a lot of the updates could be less reliable for engineering advantage and accommodating lower power architectures. And anything that goes wrong in those rare cases could be caught and corrected. So why is EXA different? I love this example, which was originally from Tom Schultes. This is, there's a floating point multiply add here, A times B plus C equals D. What takes more, doing that fuse multiply add or moving the 4 operands A, B, C, and D in and out of memory on that die, in and out of cache? Well, it turns out that going across the die will require an order of magnitude more, according to the DARPA study done by Kogi et al. The double precision floating point multiply add will cost 11 picojoules, and moving those 4 8-byte words across the chip will cost 96 picojoules of energy, an order of magnitude higher. Here are some typical energy costs today, not in 2019 according to the roadmap, and you see anywhere from 50 to 100 times more energy required to move the operands around than to do the flop within the registers. And a pico may not sound like much, it's 10 to the minus 12th, but remember we're talking about multiplying that by 10 to the 18th exa per second. So that's a mega of something per second. 100 picojoules, just the flops alone, never mind the data motion, translates to 100 megawatts if we did not improve the technology relative today. A megawatt year, as you heard earlier, costs about $1 million. And it's also an expensive use of power. You and I, as OECD citizens, use an average of about 1.4 kilowatts continuously. So 100 megawatts for this computer is the equivalent of the energy requirements of 71,000 people. Why is exa different? How have we been cruising along and suddenly hitting a block? Moore's law does not end yet. We keep addressing Moore's limitations with new technologies, new lithographies, and so forth. But Dennard's scaling for MOSFETs, a 44-year-old paper, predicted that there would eventually come to an end of this great scaling. Here you see how different elements scale as you dope as you increase the doping by a factor of kappa. You can reduce the line width, reduce the voltage, reduce the current, reduce the capacitance. You get kappa squared more computing per square centimeter at the same power density, same electrical power density. And that doesn't really stop. But what stops is the copper, the interconnect. As you keep shrinking that, the resistivity goes up. And eventually, processing is limited by transmission, as we've known for 4 decades. Also, the leakage currents become a larger percentage of the total energy. So here are the exascale architecture trends that have been reviewed by many speakers. Clock rates cease to increase. Memory capacity improves, but diverges exponentially below compute capacity. Transmission capability improves, but diverges exponentially below arithmetic capability. Mean time between hardware interrupts shortens, and billions of dollars of open source DOE and CAA and other important scientific and engineering software hang in the balance if we really want to run them on this next generation. Now, in going to 1 billion cores clocking at 1 gigahertz, 10 to the 9th times 10 to the 9th is 10 to the 18th, expanding the number of nodes of processor memory units with generous memory and generous memory bandwidth per node, that would not be a problem. We have many algorithms that follow the weak scaling of Gustafson, and if the nodes were performance reliable so that we could synchronize 1 billion of them at regular intervals, the weak scaling would not be a problem. The problem is the strong scaling going to 10 to the 3rd threads or cores per node sharing memory. And you don't need to wait till Argonne lets you onto their exascale system. You have GPUs and Intel 5s today with literally hundreds of effective cores, and this battle is fought at the small end. Then it can be easily multiplied by thousands of nodes. So our generation, the bulk synchronous programming generation, has to hand a baton to your generation, the energy-aware generation. Bulk synchronous parallelism is probably a term that you're familiar with from Turing Award winner Leslie Valiant. He didn't get his Turing Award for this, but he wrote an influential paper 26 years ago summarizing the tendency of many scientific codes to be expressible as a furious batch of computation followed by a short synchronization, then a furious batch of computation. During the synchronization, typically neighbor data exchanged or global reductions done, both the computation and the communication done in parallel. In some sense, it's not a very good use of your communication hardware, right? It's sitting idle most of the time. It's expensive hardware, you paid for it, but this was a good way of expressing algorithms in a way that made them easy to program by a data decomposition, typically particles or grid cells or intelligent agents or whatever. And iterative methods based on data decomposition and message passing are the standard petascale commodity apps today. Each individual processor works on a supposed load balance subdomain of the original, exchanges information that's lower dimensional compared to the computation, so it's a fixed percentage as we weak scale. And this model goes by many names and is well practiced in the codes that you're probably running right now. And here's just a picture of how you have more intensive interactions within a domain, which might here be in 2D, and then you have one-dimensional exchanges, and generally it would be 3D to 2 or something like that. But the scaling of the overhead is subdominant to the useful work, and this has proved to be a very productive, SPMD programming model. You can measure that not by the top 500, which is dense linear algebra, but by Gordon Bell, which is mechanics, materials, petroleum reservoirs, electrodynamics, cosmology. The Gordon Bell Prize takes sort of a pulse of real applications every November at supercomputing, and you can see where I got that factor of 1,000 every 10 years reflected in actual Gordon Bell Prize winning applications. And for many years, although this prize has not been given for some time now, there's a price performance prize which shows almost the same ratio of reduction every 10 years in the cost per installed flops capacity. But extrapolating exponentials like this eventually fails. You've already seen why in the sense of Dennard scaling. But for the last few generations, we've been able to use the same bulk synchronous programming model and make the same assumptions about who takes care of what. And hardware, we may take care of a lot of things for us at sort of a high energy cost. Exascale will be qualitatively different, and it looks more difficult, but after all, we once said that about message passing. And I think that core numerical analysis and scientific computing will want to confront these challenges to maintain relevance, to actually be able to exploit exascale. And furthermore, because it will be an intellectual stimulation. It won't just be numerical analysis anymore, but we'll have to bring in statistics and machine learning and a lot of other aspects of computational math into taking advantage of this new hardware. The main challenge is that almost all of our good algorithms are optimal n log n or order n algorithms in linear algebra, differential equations, integral equations, signal processing. They require frequent synchronizing global communication. Inner products, norms, fresh residuals, these are addictive mathematical idioms, but they tend to hurt efficiency beyond, let's say, 10 to the 5th threads, and they can be fragile for many fewer than that if you have adaptivity leading to load imbalance or hardware performance variation, and you don't have to wait for exascale for that. Just translation look-aside buffer irregularities can often spoil the reliability of a per-node computation. We already have 10.6 million cores on the most powerful system today, and we're heading towards 1 billion. So I'll put my conclusions up front, because Pete's going to cut me off at some point. There's 4 algorithmic pillars that we need to cultivate in order to get there. Reduced synchrony in frequency or in span, greater arithmetic intensity to make more use of those bytes that we've paid to move into the registers, greater SIMD style shared memory concurrency, more uniformity at the small scale, built-in resilience, algorithmic-based fault tolerance, etc. Programming models and runtimes may have to be stretched to accommodate, like the algorithms, but everything should be on the table for trades, and this is what we call co-design. 5 slides of bad news, good news in this context. We will have to explicitly control more of the data motion because it carries the high energy cost, and we're engineers after all. We're trying to optimize a computation. But we'll get the privilege of controlling the vertical data motion like we control the horizontal data motion through message passing today. Up until now, mainly it's just been rolling data in and out of GPUs that gives us control over vertical replication. But we'll get more and more tools as we declare variable types and where they can live and so forth. Bad news, good news, optimal formulations and algorithms may lead to poorly proportioned computations for exascale. Very often, flops are a proxy for bytes moved. But once the bytes have been moved, you can do a lot more flops without paying much more. And I'll end with a simple example of that in terms of high-order discretization of a CFD problem. So we may be lured into more unconventional formulations than low-order PDEs. Fully reliable executions may come to be regarded as too costly or synchronization vulnerable. Again, algorithmic-based fault tolerance. We may partition our data and our operations into two sets, those that must be done reliably in order to get the right answer, and those that can be done unreliably with a small percentage of failure, knowing that the errors can be caught and corrected. There are many examples in direct and iterative linear algebra. For instance, in direct linear algebra, the idea of doing the backsolve in lower precision than in higher precision. That's actually not a question of reliability, but floating point rounding errors. But there are many other examples where checksums or fresh residuals can be used to extend algorithms to less reliable hardware. Hardware used to be unreliable. What is that? 60 years ago with von Neumann, synthesis of reliable organisms from unreliable components. He was talking about cellular automata, but we'll have to do more numerical analysis. Default use of high precision in nodal bases on dense grids. That's how we get good truncation error accuracy to our PDE solvers today. But it's very storage and bandwidth intensive. And it's stupid to represent a smooth function without using a hierarchical basis, without exploiting continuity. It's stupid to communicate whole values, 64 bits, when only a delta of a few least significant bits has changed between successive time steps, successive messages. Generally, some hardware could help us here, remembering the last thing we sent and only sending the deltas. Finally, fully deterministic algorithms may be regarded as too synchronization vulnerable. Instead of waiting for missing data, like in the tail that Pete showed us this morning with his distribution of the time it took on each node, we might predict it using various means and continue using machine learning, for example, on the machine. If we made an error in our prediction, we can assess the impact of that error and roll back if necessary. But there's going to be a rich numerical analysis that make use of statistically inferred, quote, missing quantities in order to supplement the weakness of the hardware. Now, not everybody accepts this fourfold agenda. You can find it in the IESP and other documents. It's non-controversial that reduced synchrony and greater arithmetic intensity are summum bonum, the greatest goods. It's mildly controversial whether we will program these 1,000 cores on a node with shared memory constructs like OpenMP, or whether we will micromanage the memory in a more MPI-like way. But we will have to deal, with some extent, with that strong scaling within a node. It's more controversial whether vendors will actually deliver hardware that is known to be less than bankers reliable, right? But still, we can ask for it if we know that we can compute more solutions per megawatt hour that way by having good algorithms. So algorithms must adapt to span the gulf between aggressive applications and austere architectures. This is a full employment program for you guys, and already many postdocs at the labs that are going this way have started to be advertised. We need a lot of software at exascale. Software related to the model, to expressing the PDE or the integral equation or the molecular dynamics or whatever. Software related to the development, like how do you profile and debug with 1 billion cores, and software related to the workflow of running actual science. High-end computers come with little of this stuff. You're going to hear about a lot of it and the state of the art during this coming week. I have a small domain, which happens to be a bottleneck for many PDEs, but I hope many of you are biting off others of these very important problems. When we go to exascale, we only want to go there with optimal algorithms, order n log n. You know some examples. Otherwise, the work will grow faster than the memory, and the application will slow down. Fast Fourier transforms, multigrid, fast multipole, sparse grids, hierarchically low-rank matrices. Your generation's contribution is missing. There's been one every decade. So I'm eagerly awaiting the contribution from the 2010s. And maybe it will be in some kind of analytics and machine learning rather than in classical analysis. But with great computational power comes great algorithmic responsibility, one of my recent PhD students. Recap of algorithmic agenda. These 4 pillars: intensity, synchronization, SIMD style, algorithmic resilience, quantifying trades between limited resources. That takes you into the exciting agenda for which we go to exascale. The post-forward problems, when the hard analysis is the inner loop of an optimization, of a data assimilation, of a parameter inversion, of a UQ. Now, last year when they gave me an hour, I finished my last half hour by going through some examples of some of these solver algorithms. But today, instead, I'm going to, and I'll point you to last year's talk and slides. If you wish, you can download them right now. No, don't do it right now, but tonight. But instead, I just would like to draw a few slides out of a recent Gordon Bell submission, proudly done with Max Hutchinson, a PhD student at the University of Chicago here, and some folks at Argonne, and some folks at Intel, and other collaborators on the CFD side. And I just want to make the point that by going very high order, you can save, in the end, energy per accuracy in a typical CFD computation. Potentially less total memory required for given accuracy when going higher order, fewer grid points to get the same truncation error, higher arithmetic intensity by a long shot, and better data locality than sparse matvex, which we all know to be operating at very tiny percent of flops peak, even when they saturate the memory bandwidth. The code that we used, that Max developed for his PhD thesis, is a stripped down version of NEC 5000, the famous Argonne spectral element incompressible flow code. It's been used for a number of grand challenge applications. It's used a lot in designing cooling systems for the nuclear core in conventional power plants. Max wanted to see what you could do with a stripped down version on many core architectures. Here's an example of a classical use of a NEC 5000 by Andrew Siegel with some uranium pins missing, but the fluid mechanics around them. So one of the main bottlenecks, of course, is to invert the Poisson operator in both the transport equations and in the pressure Poisson equation. The nonlinear terms in this code are treated explicitly. So you have a lot of Poisson solves between some very parallelizable explicit updates. So we ran it on 16-core Haswell, 18-core PowerPC, namely SHAHEEN at KAUST and Mira at Argonne, ranked respectively number 10 and number 6 currently. And we tested it on KNL, pre-release testbed, and I'll have a couple of slides on that, and you can find details in these papers, and these slides will be online. By the way, I have to say, we didn't make finalist. When you go up against a 125 petaflops machine that came out of nowhere and took 3 of the 6 Gordon Bell slots, you're not so sad about that, but it was a fun run. And what I show you here is the order of the finite element ranging from 4 to 32. And on the corresponding to this left plot, the bars indicate the gigaflops, and corresponding the lines are the gigabytes per second. And this is on SHAHEEN, or on Caswell, using 2 tricks: just-in-time compilation, libx SMM from Intel, and non-temporal stores, which is a way of writing directly to memory and skipping the cache refresh when you know that you won't be caught reading that cache element again soon. And there's 2 trends here. The first one is that high order lifts all boats in terms of the exploitation of the hardware that you're paying for anyway. And the other thing is that within one order, there are some advantages incremental to those extra little tricks of NTS and libx SMM. So here's the equation system. It's a simple Rayleigh-Taylor instability. Here's Mira and SHAHEEN compared. I won't go into details. I want to make one point, which is this slide. This is an 8th order method, and this is a 16th order method. And there's a factor of 8x in core hours between them to get the same accuracy. The left-hand scale is accuracy down is good. Here's a 14th order method and a 28th order method. Again, almost an order of magnitude of saving of core hours to get the same accuracy for this computation by going extremely high order. Furthermore, the thing strong scales and weak scales, if both strong and weak scaling would show up on these 2 plots as horizontal lines. And you're getting a good percentage of the theoretical peak of a supercomputer, which is not common these days. If it was a sparse PDE with conjugate gradient, you might get 1 to 5% of peak, but here it's a hefty percent of peak. Here is an interesting comparison with the new Knight's Landing. The top is core per core for a variety of different cell sizes, and the bottom is the full Intel Phi versus a double Haswell, 32 cores, and this is parity. So in every case, the Intel KNL is now able to beat the Haswell. That wasn't the case for KNC. We've looked at other fluid mechanics problems for that. And finally, I just point out there's about a 20% savings in total energy. So this is power versus time. So the area under the curve is the energy using libxSMM versus the compiled code on SHAHEEN. I did a little calculation. The area under this curve at a 12-cent kilowatt hour is worth about 36 bucks. So you do that run many, many times. Treat yourself to dinner for the hard work that you did to go high order and use the best performance tricks. So just the top bullet, high order methods are an example of increasing the arithmetic intensity and SIMD-like concentration of flops within a node after the memory motion cost is already paid for. They don't work for all problems. If I had shocks in this problem, there would be some domains where the high order would not be useful. I'd have to drop back to low order. So they're not a solution for everything, but they're something to be looked at. And you should always crank up the order based on this particular narrow view of life until you're saturating the floating point capabilities. On Blue Gene Q, this is order 15. On the Haswell, it's order 31. Very surprising. We thought that would surprise the Gordon Bell people and delight them, but evidently, and there's a lot of other exciting news coming to Gordon Bell this year. So skate to where the puck is going to be, and thank you very much.
In the beginning of the talk, we talked about the algorithm called ACR. You talk about, yes, I don't know if I heard it right, but you said it is used to be n log n squared, but now it's done on some GPUs, and we use n squared algorithm, which is faster.
No. In that case, actually, there is a complexity reduction which you go for. The traditional method without hierarchically low rank matrices to compress the dense shear complements would be order n squared. So there's first a complexity reduction to order n log n or order n log squared n. It's actually n log n in memory and n log squared n in flops to use those H matrices. So in that case, you're following the right direction by the old arrow of minimizing flops. But the point is that that all those there's actually there's a k squared, which is the rank of the off-diagonal blocks that I didn't talk about. K is normally adequately small enough so that once if you have a big cache, you can do all those flops with very little extra cost. So it's really shifting work down to the small scale where it's in residence and low cost to do a lot of flops for the local SVDs or whatever your low rank technique is.
So in terms of flops, are we doing more flops or less flops?
Well, actually, in that case, you're doing less flops, but within a node, you are doing less flops because you're getting a big reduction from n squared to n log n. Sometimes we go the other direction in total flops, if they're free. But in this case, you're getting both. You're getting a flop reduction, and the flops that are left to do are relatively concentrated in terms of data locality. Thank you for that clarifying question, because there were examples of both sides. So without your question, I might have left the wrong impression.